Thank you. Alright, so welcome back to the last session of today. So more torture, right? Alright, so what we will prove is a generalization of Tutte's theorem, and the generalization is the Tutte-Berge formula. Right? So let's do a quick recap. What we discussed in the earlier part, the second part today, is that for any graph, if I give you a matching M and a set of vertices S, then here is an inequality that holds. Okay? I'm not saying this inequality is interesting for every set of vertices. It may be very uninteresting for certain sets of vertices. It may give you something more than n by 2. Of course, every matching has cardinality at most n by 2. But it is an inequality for every matching in any set. You all agree? And the way we arrived at this is we actually switched the focus to the number of exposed vertices, and we noticed that the number of exposed vertices has to be at least 7 minus 3 in this case, and then we did the arithmetic to get this. Yeah? Okay. And what is really interesting is that, of course, something trivial, sort of, is I can maximize this and minimize this, and this still will hold less than equal to. Yeah, that is clear. If it holds for every set, every m comma s, it also holds for an m that maximizes the LHS and an s that minimizes the RHS. Yeah. But what is really interesting is that it's equality. This is not clear at all why it should be true. Right? This is the one that needs a proof. Okay. And another way to, so this is the Tutte-Berge formula, proved sometime in the 1950s, basically Tutte's theorem with more bells and whistles, and then gives Tutte's theorem as a consequence. Cool. So this is an equality. So the way we will write this down is we will define this thing called a barrier. It's any set of vertices such that this quantity is equal to the cardinality of the maximum matching. So this is called the matching number of a graph, and we will use the notation alpha prime. So you may say y prime is the same reason why I use chi prime for edge coloring in the beginning, in the first part today. So observe that a stable set in a graph becomes a matching in the line graph. Right? Everybody knows what a stable set is, independent set. If I take an independent set in a graph, in the line graph, that corresponds to a matching. So the stability number, the cardinality of a largest stable set, is generally called alpha g, and therefore the matching number we'll call it alpha prime of g. Yeah? So let's compute the alpha prime of this graph. This is my graph G. I've given you a matching M. The question is it a maximum matching or not? Let me label the vertices while you think about it. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Yeah, graph 122 vertices. Yeah. So I've given you a matching M. If it is not maximum, you will just show me a larger matching, and I will check, and I'll, yeah. But what if it is maximum? What will you show me? Is there something you could show me to convince me that this is actually a maximum matching? Is it or is it not? I don't know. Actually, I don't know. Sorry. Which set?
Barrier set.
Barrier. Can you show me a barrier?
19, 20, 21.
Yeah. Conveniently numbered 19, 20, 21. Thank you. Observe that if you delete 19, 20, and 21, how many odd components do you get?
5.
1, 2, 3, 4, 5. You get 5 odd components. So you deleted 3 vertices, you got 5 odd components. 5 minus 3 is 2. How many exposed vertices in this matching? 2. The number of exposed vertices, m exposed vertices, is 1 and 4. Therefore, you have a matching M with two exposed vertices, and the number of odd components minus this is also equal to 2 for the set S in orange 19, 20, 21. Yeah. Therefore, in any matching you will have at least two exposed vertices. Because in this matching there are exactly two exposed vertices, this is a maximum matching. Yeah, that's a Tutte-Berge theorem. Yeah, does the theorem make sense? Yeah. So it's stated it's stated as a single line. This is the shortest theorem statement. Of course, all of the stuff is hidden in the definitions. If the graph is a barrier, you would think this should be like a one-line proof. Oh well. Welcome to modern mathematics. Okay. Okay, questions, concerns regarding the statement? Is everybody okay with the statement? Yeah? And do you all agree that if we prove this, we have proved Tutte's perfect matching theorem? Right? If you are not convinced, please do it as a DIY before tomorrow's session. So DIY Tutte-Berge implies Tutte's perfect matching theorem. Yeah? And we have seen that Tutte's perfect matching theorem has cool consequences. Every two connected three regular graph has a perfect matching. Not only that, it is matching covered. Every edge belongs to some perfect matching. So we will prove this more than very well. The Tutte-Berge formula. An announcement for all of you. Okay, so yeah, in general, I want to point out that if I have given you a barrier, a maximum matching will basically look like this. Any maximum matching, what it will do is, it will match some of the odd components, one vertex each, into the barrier, and then the rest of the matching, basically you will have all the vertices here matched, except for this one which is matched outside. Same here, same here. These are odd components that will contribute one exposed vertex, and the even components will basically have a perfect matching. Every maximum matching will look like this with respect to any fixed barrier. Right? There is no other way to attain the equality we want. Right? That's the only way to attain equality. Okay, good. Right, so now let's prove the theorem. So the proof we will see, hopefully we will finish it today, let's see, will be very slick, which is good and bad. Good is it's a slick proof, it's an elegant proof, blah 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 blah. The bad thing is it doesn't tell you anything about how long it took for this proof to be arrived at. Right? So the proof we will see today is probably the work of decades by people, various people, to reach this level of simplification, both in terms of the mathematical ideas and also just in terms of improving the write-up. And the two processes cannot be separated and shouldn't be separated. Right. So we'll see a proof by induction on the number of vertices.
I think I'm just done.
Sorry?
I think I'm just done.
You're done?
Like
Proof?
just induct on the order even component. And if you have something else, you can just add that to the value.
I see. Think about it. I am not fully convinced. See if you can write down everything. We can discuss at the end. Right? I may not have the bandwidth to process all of this in the lecture itself. Right? But yeah, we can discuss at the end or tomorrow. So we'll prove by induction. Prove by induction. It takes a while to actually prove by induction. All the proofs that I know. So let's talk about some concepts. So let's think about this quantity, the matching number of a graph. Since we are going to induct on the number of vertices, and since the definition of a barrier has this embedded in it, we should probably understand what happens to this quantity when we delete a vertex. Right? Good thing is, one very good thing about this theorem, it's about all graphs. Very rarely do you come upon statements about all graphs. Typically the statement is about connected graphs. Then you prove it for connected graphs, and then you may get a statement about all graphs using the statement about connected graphs. But here, the statement itself is about all graphs. Good news is, if I delete a vertex from a graph, I get a graph. This is very nice, because then I can just apply the induction hypothesis without using any fancy tools. For example, if you are proving something on trees, what do you delete? You delete a leaf, not an arbitrary vertex. Right? That's the point I'm trying to make. For a graph, if I delete any arbitrary vertex, I get a graph. Okay, that's good. So let's think about what happens to this quantity when I delete a vertex. I want you all to think about this. How much can it change? How much can the matching number is the cardinality of a maximum matching. How much can it change by if you delete a vertex? Think about it and raise your hand. Maybe write down on your notebook so that everybody has a chance to think. Yeah, how much does it change by? Okay, how much does it change by? Okay. Yeah. Think about it. So it may not change at all. That's one possibility. One possibility is that it is equal to the matching number of G. What's the other possibility? Maybe raise hands. Somebody I didn't talk to already. So if it doesn't stay the same, what happens to it? How much does it go down by? 1. Yeah? Everybody agrees?
Yeah.
Either it stays the same or it goes down by 1. You all agree?
Yeah.
When it stays the same, we will call the vertex inessential. When it goes down, we will call it essential. Yeah? Why does it actually, before we do that, what does it mean to stay the same? If it stays the same, what does it really mean? That in the graph G, there is a matching M, there is a maximum matching M for which that vertex is exposed. Is that right?
Yeah.
Yeah? So it actually, let's write down. This happens if and only if G has a maximum matching M such that V is M exposed. You all agree?
Yeah.
And when does it go down? The negation of this, right? Which means for every maximum matching, this vertex is saturated. Yeah? Yeah, saturated. Yeah? So, this happens if and only if for each maximum matching M of G, V is M saturated. You all agree? Yeah? Therefore, we will call these vertices essential or inessential. Right? Which one is inessential? This is inessential because I can keep this fellow M exposed. So these vertices are called inessential. And these are called essential. Yeah? Okay. These are the essential vertices. These are the inessential vertices. Okay. So let's ask some basic questions about these concepts. I want you all to think about what are those graphs in which every vertex is essential. Think about it. Each vertex of G is essential if and only if something. Each vertex of a graph is essential if and only if something happens. Okay? You write it down and just call me. What does it mean for every vertex to be essential?
There's a perfect match.
So if you delete the vertex, left can the size of a maximum matching go down by 2. You take a maximum matching. If it doesn't match the vertex G, then the same thing as a matching G minus 2. If it matches the vertex V, then remove the edge. That is a matching of the smaller vertex. So you still have a matching with 1 less edge. No, yeah, number of edges and maximum matches. Yeah, so everybody is figured out? Yeah, every vertex being essential just means that the graph has a perfect matching. Yeah, you all agree? This is the same as saying that G is matchable. Yeah? Okay? So, what we will do to prove the Tutte-Berge theorem, either the graph has an essential vertex or it has no essential vertex. Every vertex is inessential. Yeah? We'll have to also understand those graphs. So here is a question which we are not going to answer yet. The question is, what is the analogous statement for inessential? Each vertex of a graph G is inessential if and only if blah. This blah happens to be much more interesting. It is definitely not trivial. Okay? We will answer this question eventually. We will show that these graphs have a barrier. We will try to understand these graphs. We will prove that they have a barrier. Because if we understand them well enough, then maybe we will just be able to see, blah is a barrier. Finish. Right? So, if we deal with this, this is going to be our base case. That leaves us with the case where the graph has a vertex that is not inessential, which means the graph has an essential vertex. That's going to be our induction step. And we'll finish off the induction step first. Yeah? So, let's see. By induction on n. N is the number of vertices, always. Yeah. First, suppose that G has an essential vertex. Supposing there is a vertex V that is essential. I want you all to try this. See if you can finish off the proof. Consider the graph G minus V. It has a barrier. This implies that, well, by induction hypothesis, G minus B has a barrier. Right? What do you know about the, so what you should do is, you should write down the definition of barrier. What does it mean for G minus V to have a barrier, right? It means something in terms of alpha prime of G minus V, right? So just write it down. See if you can finish the proof yourself for this case from here. It's just a bunch of manipulation. If you can see it, just write it down and just call me. Let's say the barrier is B. B is a barrier in G minus V. Right? What does that mean? Definition of barrier. It is a subset of vertices for which this fellow holds. Right? So what is the number of vertices in G minus V? It's n minus 1 minus the number of odd components in G minus B minus cardinality of B plus the cardinality of B divided by 2. This fellow is equal to the matching number of G minus B, which is, okay, let's just write down matching number of G minus B. Alpha prime of G minus V. Yeah, that's what a barrier is by definition, right? What we want to do is we want to show that G has a barrier. Right. So what are the possible sets you will try? There's only so many possibilities in life that you can try, right? So you have to do something kind of straightforward. I claim that from B, the barrier of G minus V, I claim that I can construct a barrier for G. So just try something and see what happens. So DIY, use B to construct a barrier of G and of course prove it. It's the least fun part of the proof. It just goes through.
See, I'm not ready now. I think I'm just working through the cases.
Okay, anyone else? Right, so just try some set. There's only so many things you can try using B. Right. Either you try B itself and see what happens. If B doesn't B, then you try something else.
He's supposed to be stable. I don't know. Independent. I can not adjust with it. I know what I have got. Could be a big one.
Yeah? Everybody got something? Yeah? Did you try the natural sets to try? Yeah? Does B plus V work? Yeah? Do you all agree that B plus V just goes through? Yeah? So basically the desired barrier is B plus V. And just do the math and see that it all goes through. Yeah? Okay? So if in this case we are done, proof is finished. Yeah? But we use the fact that the graph has an essential vertex. So in this case we are done. Yeah? Claim B plus V is a barrier in G and prove the claim. Routine. Yeah, I'm not going to write it down. If everybody is okay with that. Yeah? Okay, good. So we are done with this case. What remains is when every vertex is inessential. Yeah? What we will do is, we will try to actually understand what these graphs are. What are the graphs in which every vertex is inessential? Once we have a good enough understanding of these, we will just see that these have a barrier. We are done. Yeah? So what are those graphs where every vertex is inessential? They are those graphs where every vertex is inessential. Okay. Something more interesting than that.
If you remove a vertex, the maximum, like alpha prime G is still the same, no matter what you remove.
That's right. That is true.
Where the graphs whose connected components have the same property.
True. That's a good point. Observe that every vertex of a graph is inessential if and only if each component has the same property. Do you all agree?
Yeah.
Okay. This basically suggests that we should probably deal with connected graphs. Okay. So what we'll do is We will answer this question for connected graphs. Every vertex of a connected graph G is inessential if and only if blah. We did not do that for the earlier case. There we just said for every graph, right? But here it turns out going to connected graphs is actually nicer. So we'll go to connected graphs and try to understand what are those connected graphs when every vertex is inessential. Right? Inessential just means that for every vertex there is a maximum matching that leaves that vertex exposed. Okay, sure. Can we say something stronger? Turns out, anybody else wants to take a guess? I mean, it's not that easy to take a guess unless you've tried out a lot of examples. Yeah.
Every connected component is K2 and plus 2 has C and C.
That's too restrictive. So every connected component. So here is a counter example to your statement. This graph has the property that every vertex is inessential. Please check. Please check that every vertex of this graph is inessential. Yeah, you agree? Okay, what is the cardinality for maximum matching in this graph? 2. Number of vertices is 5. So it is n minus 1 by 2. Yeah? Turns out this is true. If every vertex is inessential, then for every vertex you can delete that vertex and the remaining graph is matchable. This turns out to be a very important class of graphs in matching theory. They are called hypomatchable. So they are not matchable, but they have a very strong property. For every vertex there is a perfect matching in the graph obtained by deleting that vertex. Or in other words, there is a near perfect matching in the graph that just leaves that vertex exposed. This you can do for every vertex. Turns out that these are exactly those graphs. So what is a hypomatchable graph? It is a graph for which if I delete any vertex, the remaining graph is a perfect matching. So, for each vertex V, G minus V is matchable. An unfortunate thing is that according to this, the null graph is also hypomatchable. Null graph means a graph without any vertices. So I assume that the graph is not null. Non-null means that at least one vertex. Yeah? And what we will prove is that a connected graph has this property if and only if it is hypomatchable. Quick question. Can a hypomatchable graph be disconnected? Can a hypomatchable graph be disconnected?
No.
I know.
Make a drawing, make an example. Can a hypomatchable graph be disconnected? Just to get some familiarity with it.
Because every component that we are
Right? Do you all see that hypomatchable graphs by definition are required to be connected? Yeah? Yeah? Okay. Yeah, but the point is that if you remove connected from here, then you have to say that every component is hypomatchable. So a graph is hypomatchable, or sorry, a graph has this property, every vertex is inessential, if and only if each component has this property. Right? So what you will get is just a union of disjoint union of hypomatchable graphs. That is the answer to the original question. Well, we haven't proved it yet. Right? So what we will prove is this result. This is to be proved. Supposing we prove this, let's suppose we assume this to be true. Can we now finish the proof? Can you now try to finish the proof? Assume that statement to be true. Each vertex of a connected graph is inessential if and only if the graph is hypomatchable. Can you now try to finish the proof? What about graphs that don't have any essential vertices? What is a barrier there? Think about what is a barrier in a hypomatchable graph. Try to get a barrier in the graph I drew earlier. What was the graph I drew? I drew this graph. Try to find out all the barriers of this graph. That's a fun exercise. What are all the barriers of that graph?
The empty set. I have done this again. Like for a hypomatchable graph, only the empty set.
What are all the barriers of a hypomatchable graph? We'll just find one barrier first. Right? Let's try to understand what it means to find a barrier, right? Let's just try to get more familiarity with the definition. So barrier will basically leave you, when you delete that set, the number of odd components you should get should be exactly the difference, that difference between the set and the number of odd components should be exactly the number of exposed vertices in any maximum matching. Okay? This is a hypomatchable graph. You delete any vertex, it's a perfect matching. So the number of exposed vertices is 1. In any maximum matching, the number of exposed vertices is 1. So barrier is a set of k vertices for any value of k you like, so that when you delete those k vertices, you get exactly k plus 1 odd components. That's what a barrier is for this graph. Right? So that's the way to think about it. You delete that set of k vertices, you should get exactly k plus 1 odd components. Then it is a barrier. Otherwise it's not. Right? So now you can think about what are the barriers of this graph.
Can we say k less than half of m?
Sorry.
Can we say k less than half of the k's of m?
Okay, so what's the barrier of this graph?
On any of the vertices.
How many odd components you get when you delete any vertex?
I can see one value, but I don't see the value.
That's the point of the exercise. Yeah. Anybody else? Anybody wants to discuss? Did you figure out the barriers of this graph? Right? Is anybody able to find an interesting barrier? For some definition of interesting?
The only definition.
Right? There is no interesting barrier. The only barrier in this graph is the empty set. That's a barrier. We never said it is a non-empty set. Yeah? Okay. In hypermatchable graphs, in fact, the only barrier is the empty set. But we don't really need that. We just need the existence of a barrier. Convince yourself that in any hypermatchable graph, the empty set is a barrier. Yeah, is that clear? Not just for this, but for any hypermatchable graph. So therefore, if your graph has no essential vertices, there is just a disjoint union of hypermatchable graphs. And observe that in the disjoint union of hypermatchable graphs also, the empty set is a barrier. In fact, if G1 and G2 are two disjoint graphs, B1 is a barrier in G1, B2 is a barrier in G2, then B1 union B2 is a barrier in G1 union G2, the disjoint union. So that is a more general statement. So therefore, if your graph has no inessential vertices, then if we prove this result, we are done. Those graphs have a barrier. The empty set is a barrier. Okay? So now the only thing that remains to prove is this statement. If every vertex of a connected graph is inessential, then the graph is hypermatchable. The converse is clear. If a graph is hypermatchable, do you all agree that every vertex is inessential? That just follows from the definition. Yeah? So the converse is clear. We just need to prove one direction. Good.
Why is 0 the only one?
Sorry?
Nothing.
Okay. So let's just write down what we need to prove. The only thing we need to prove, let me get rid of this fellow now.
It follows from the Tutte-Berge formula. It follows from that.
Okay. So the only thing that remains, G is a connected graph. The null graph is disconnected to me, therefore it's out. It's a connected graph whose each vertex is inessential. And what we want to conclude is that G is hypomatchable. This is what we want to do. To prove G is hypermatchable. Yeah? Okay, so before we proceed, let me just make sure we all agree. If we prove this, we are done with Tutte-Berge theorem. Therefore, we are done with Tutte theorem, and therefore we are done with everything we proved today. Yeah? Because that's the only thing we used in life. Okay. Again, the proof we will see of this is a hyper elegant one, to the point where it kind of is a bit like what? Where is all the years of hard work? Where did it disappear? I don't know. Okay. Let me ask you. If we prove the following statement, for any maximum matching M and any two distinct vertices U and V, at most one of U and V is M exposed, then are we done?
At most one of your or at least one of
At most one.
Yeah.
If we prove the statement, let me write down the statement.
Should be
For every maximum matching M of G and distinct vertices U and V, at most one of U and V is M exposed. Supposing we prove this statement, are we done? Think about it. Will it be enough to prove this statement?
Yeah.
Yeah? Everybody agrees? This is good enough. We will prove this. Yeah? It suffices to prove the following statement. Yeah? For every maximum matching M and distinct vertices U and V, at most one of these two fellows is M exposed. If we prove this, we are done. Let us proceed by contradiction. Supposing this is not true, that means there are pairs, there are triples M, U, V for which this statement is false. You all agree? If this statement is not true, then there are triples M, U, V for which this is false. Amongst all such triples, we will choose one that minimizes the distance between U and V. Yeah, can we do that? Is that okay? Yeah, shall we do that? Suppose not. More colors, why not? Suppose this is not true. Amongst all MUV that violate the above, choose one such that the distance in the graph G between U and V is as small as possible. Yeah? Is that fair game? Can we do that? Yeah? Of course, there is a way to write this using induction, but I personally prefer the minimal criminal method. Let's choose the criminal who is minimal as per some whatever minimality. Yeah? Also known as a minimal counterexample method. Right? So we'll do this. Right? So let's draw a shortest path between U and V. Right? Yeah, by distance I mean the length of a shortest path joining the two vertices. Yeah. So I need some more space now. Let me create some space here because anyways we have proved all of this assuming this statement, so who cares? Okay. This is the fun part of the proof. Okay, let's make a drawing of a path. Okay, that's good enough. This is U, this is V. M is going to be my perfect matching in the pink color. Okay? So, if you consider the matching M, it will leave U and V exposed. Is that correct? U and V are M exposed. When a vertex is exposed by the perfect matching, I will put a circle of that color around it. Okay, so circle, pink circle means the vertex is M exposed. Yeah, where M is the pink matching. Let me ask you, can the length of this path be 1? Single edge? No, right? Everybody agrees because then M would not be a maximum matching. Right? The length of this path cannot be 1. Okay, so let's say P is a shortest path, a shortest UV path in G. What we observed is that the length of P, which is the number of edges, not the number of vertices, the length of P is at least 2. It can't be a single edge. That means there is at least one internal vertex in the path. By internal I mean vertex that is not U or V. Right? So let me consider such a vertex W. What can you say about the internal vertices of this path?
Then
as per our choice.
matched.
They are all
Matched.
M covered, M saturated. You're right? Yeah? Because we chose to minimize the distance between U and V, it follows that all these fellows are M saturated. All internal vertices. We know there is at least one because the length is at least 2. All internal vertices of P are M saturated. Right, so what I will do is, I will just put an edge over here. This edge could be either this edge or this edge. But there is a matching edge. There is a pink edge incident at this vertex. Could be in the path. Yeah? Okay. Alright. Clearly, the goal is to arrive at a contradiction to our choice. Right? We want to do that. So that means that we must construct another triple n, x, y, whatever. So that n, x, y contradicts the original choice of m, u, v, right? Okay. So that means we want to probably construct another matching. Okay. It's easy to construct new matchings if you have at least 2 matchings. If you have only one, then there's not much you can do in life. But if you have 2, then you can play some games with them, also known as alternating games. Yeah? If you have 2 matchings, then you can play some games, right? So we need a second matching, ideally, right? So we know that the original graph has the property that every vertex is inessential. So what shall we do?
Oh, they can move one vertex.
Which vertex?
W.
W. Let us throw away W and take a maximum matching in the remaining graph, or take a maximum matching in G that does not saturate W. Is it okay? Let's do that. Consider a maximum matching since each vertex of G is inessential. There exists a maximum matching N of G such that W is N exposed. This is going to be my yellow matching. Okay? So my yellow matching is going to be some maximum matching that leaves W yellow exposed. Yeah? Good. What can we say about U and V with respect to N? Given our original choice, what can we say about U and V given our original choice of M, U, V?
They have to be
Matched.
matched.
They have to be saturated. If either of them was exposed, then you would choose that fellow and this fellow, and now you have a contradiction to the distance business. N, U, W will contradict the choice of M, U, V. Yeah, fine. Therefore, these two fellows have to be matched. Could be an edge in the path, I don't know, but they are matched. That is what I'm indicating. Yeah, so we have these two matchings, M and N.
It can't be an edge in the path.
It can't be an edge in the path, is it?
Yeah, it'll shorten the path, right?
It will shorten the path. If it is an edge like this,
Unless it's the shortest edge, which doesn't make any difference.
why will it shorten the path?
Like if say it's an edge ahead of that, ahead of the immediate neighbors,
Yeah.
ahead of the immediate neighbors.
Okay.
Then like it will shorten the path by one step at least, right?
For what choice? What is your?
Because M, U, V is minimal path. U,
Okay.
V is your minimal path. So if
Yeah.
there was 1 or 2 steps ahead at least, You can just remove those two edges and add this edge.
Okay, so you're making some changes to the matching.
Yeah, like it would, like all the matches are outside there.
Okay, sure, that might be, yeah. But anyways, I won't worry about where it is. Yeah, so it could be anywhere, we won't care about it. We'll just write a general argument that finishes off everything.
I think what you're saying is that because it is the shortest path,
Yeah.
no vertex in the path joins some other vertex in the path. The path is in
Oh. You mean it can't be like this?
Yeah, exactly. Yeah.
This, okay.
It can be its immediate neighbor.
That's just because of the path being shortest
Path
between
being
U and V. Yeah, that's right. Because this is the shortest UV path, it is actually an induced path.
Yeah.
There are no chords in this path. That's right. No, I thought you were using the choice of mu comma v, but you're just using the fact that p is the shortest path.
Yeah.
Got it. Now I understand. Yeah. Good. Thank you. Yeah. So we have these two matchings, m and n, and now I claim that you can play a game to arrive at a contradiction. So try playing that game yourself. Yeah, and then we will discuss with everybody. So, so what do you do when you have two matchings in life? That's the main question. When you have two matchings, what do you do? You consider them. What was the word? Switch. Before that, what do you do? Consider their symmetric difference. That's the main thing. In life, when encountered with two matchings, immediately consider the symmetric difference. Right? There is only so many things you can do with two matchings. Right? If you don't like symmetric difference, like I did not like them once upon a time, consider the union. Union will just put some K2s, some pink, yellow K2s will be there. In the symmetric difference, they disappear. Not a big difference, right? Yeah. So maybe what I want you to do is, I want you to think about the symmetric difference of two matchings and see if you can finish the proof. DIY. Consider n symmetric difference n and finish proof. And if you haven't done this kind of stuff before, then you should just think about what does a symmetric difference of two matchings look like. Right? So you are going to take the edges that are pink but not yellow and the ones that are yellow but not pink. And just consider, keep all the vertices, don't throw away the vertices. Vertices are friendly. Just consider these edges and try to draw the components of this graph. What can these components look like? Okay. And if you have something to share, just raise your hand and I'll come and talk to you. Until when do we go on? 5:30. Oh, we have 20 minutes. Enough time. Okay. So if you have an answer to this question, you can already tell me. What does each component of this graph look like? And then we will discuss further. So what does each component of this graph look like? Just raise your hand and then we'll come and talk to you. So if you are stuck, just pay attention to the degrees of the vertices. Look at any vertex and think about what happens at that vertex. That's the way to go. Draw and color. If you are stuck in anything, draw and color. And you will get unstuck.
What do you mean? It can't be because the gateway is different. What color? You talk about that for just do एक pink color का भी है और yellow color का भी है. उसमें तो pink color है तो क्या होता है? Pink color yeah, but you are correct.
Okay, anyone else?
You so like when was what is of W and correct treatment what is equal to numbers strategies. You have because there are only I thought it can be in the big mind. Because you will be in
Okay, anyone else?
You can have these, right? I'm doing computer. I was a computer. You're giving input. Someone input.
Right, so there are multiple things going on here. One is the symmetric difference of two matchings. That's one question, right? But here, of course, we are looking at a special case. We are considering two maximum matchings. And of course, another interesting case is when the two matchings are perfect. But that's not the case here anyways, right? Because we have the property that there are exposed vertices. So these are not perfect matchings, but these are maximum matchings. So for the symmetric difference of maximum matchings, can you say something more? Right? So in general, for two matchings, what is the answer? What do you get every component as? If I just take two matchings M and N, What is the symmetric difference of them? What is each component?
Cycles of
Cycles or paths? And what are the lengths of the cycles? Even. The cycles are of even length. The paths you cannot say anything for matchings. Okay, could be even length, odd length, doesn't really matter. Right? Anything is possible. Now the question is maximum matchings. In the case of maximum matchings, can you make it more restrictive? Right? Can you think about, so the cycles will again be even and those can exist, that's not a problem. But can you say something more about the paths?
I don't understand how you can have a path.
Make an example.
I don't understand.
It's the endpoint of a path.
Right, so you could, for example,
Oh, when you have an exposed vertex,
here is a graph.
there will be like finite number of like 2 or 3 paths only, right?
Well, I don't know about that. I don't think that is true. But anyways, here is an example, right? Here is a graph that is just a path, and here are two maximum matchings. Symmetric difference is the
That's
path.
right, so it's-
Only for that to be two digital paths. Oh yeah, what should be the I can't just
So does anybody see something about the parity of the paths? Right, everything boils down to parity in life.
Even number of edges.
Sorry?
Even number of edges.
Even. Do you all agree? The paths are going to be even. The reason for that is supposing you had an odd path. Let's just draw an odd path. This is an odd path. This is a path in the symmetric difference. That means this fellow is exposed with respect to the pink matching. And this fellow is also exposed with respect to the pink matching. Yeah? And all the other vertices are saturated with respect to both matchings. Now I claim that one of these two matchings is not maximum. One of the graph may have more components. The symmetric difference may have 1,000 components. I don't care. But this is one component. I claim that one of the two matchings is not maximum.
Oh, pink wala.
Yeah? Pink wala. Pink wala is not maximum. Yeah? You all see that? Because I could simply replace the pink edges by the yellow edges in this component and keep it unperturbed in the rest of the place. Oh wow. Okay. Alright. We are still recording, I guess, in the darkness. Alright. So the light comes back soon here, is that how it works? Interesting. We are after all limited by the physical world that we inhabit.
No, it's better than this. The hair is
Good, bad.
Hey, bro's coming by head.
And this forces you to think about it in complete terms. except that now you can't see the colors. You have to imagine.
I can't see black and
How
white.
does even pass the find out
Nishad,
Yes.
till the light comes back, could you maybe just mentally tell your argument?
It won't be recorded. But maybe I should just give enough hints so that you all can finish it yourself, right? So we have these two matchings, M and N,
Phoenix voices that is
right?
given.
And we want to get a contradiction to the choice of M, U, V. Right? M leaves U and V exposed, and we have this shortest path, A shortest path joining U and V, P, and we chose an internal vertex W, and because the graph is hypermatchable, we chose a maximum matching N that leaves W exposed. Oh, good. All right. Okay. So we start the recording again. Can you start the recording while we wait for Ravindra?
Did we stop it?
I think we might have. I'm not sure. Let me just check.
It's going.
Yeah, it's going on. Oh, it captured the darkness. All right. Okay. So back to the situation we are in, right? So we have two maximum matchings. M U V was chosen so that the distance between U and V is minimized. Blah blah blah, all that stuff. And then we took a shortest path P. This is the path P. And we chose an internal vertex. We know there is an internal vertex because the path is length at least 2. And we chose a maximum matching that leaves this vertex exposed. That is our N. Right? So what we are going to do is we are going to consider the symmetric difference of M and N. And we observe that the symmetric difference of two maximum matchings is just a bunch of even paths and even cycles. Right? Okay. So we want to switch one of the matchings on either one of the paths or the cycles and get a contradiction. Yeah? Okay. So consider the path that contains, do you agree that U, V and W, do you agree that all three belong to paths?
Yeah.
Yeah? Because their degree is 1 in the symmetric difference of M and N. And in fact, they have to be ends of paths because they are degree 1. They can't be internal vertices of paths. Right? So U, V and W are all going to be ends of paths in M symmetric difference N. Yeah? Consider the path that starts at W, that contains W, which means W will be one of the ends. Right? So consider the path Q in M symmetric difference N that contains W. Yeah, there will be some path that contains W. Let's draw that path. So it will be a pink yellow path. W is starting at pink. So it will start at pink, then it will be yellow, pink, yellow, pink, yellow. Yeah? And this is the vertex W, which is yellow exposed. And the other fellow there is pink exposed. This is the path Q in the symmetric difference of these two. It has nothing to do with this path P, right? So don't think that this path is disjoint from this path or anything. I don't know how this path Q interacts with this path, but I also don't care about it. Right? I'm just looking at this graph, M symmetric difference N. Here we have drawn all the edges of the graph. So the edges of the path, we don't know whether they are pink, yellow or something. Okay? So my claim is that on this path Q, we can play the switching game and get a contradiction. Switch what? I don't know. Think about it. I claim that you can switch one of the two not perfect. You can switch one of the two maximum matchings on this path and keep it the same everywhere else, right? And I claim that the new maximum matching you will get and some two vertices x and y, I don't know what x and y are, that will contradict the choice that we had. Right? So the question is, what is this vertex? Which vertex could this be? It could be this vertex, I don't know, let me call it x. X could be u,
Or B.
x could be v,
Or it could be something else.
or something else. I don't know. Right? But it cannot be both u and v. That's a trivial statement, right? Because u and v are distinct. X cannot be both u and v. Yeah? That is also interesting. So it's not one of them. Let's suppose it is not u. Let me assume without loss of generality that x is not equal to u. X is not equal to u. Then I claim that we can get a contradiction. Can you try to do it yourself? And then just raise your hand and see if you figure out. Yeah. See if you can come up with a new matching M star or whatever you like to call it. And two vertices y and z, because I already used that x. Right? And that should contradict your original choice, M U V. Yeah.
Supposing the path is small, so it will start at single and supposing it starts at the and at first then the yellow matching on this path, I will take the pink and check. Which color? And no, switch color and then on that path. And then you would look at that.
Okay, does everybody kind of see where this is going? Yeah? We are just going to take one of the two matchings, M or N, which one I don't know, we'll see. And we are going to switch it on this particular path. Right? And right, so let's see what happens. If I take the yellow matching, the yellow one is the M. If I take M and switch it here, only on this path. So instead of the yellow edges, I'll choose the pink edges on this path. Right? If I do that, then what will happen? What will be exposed? No, I want actually W to be exposed. So I want to take the yellow edges here and the pink edges elsewhere. Yeah, yeah. So I'll take the pink one and switch it on this path. So let's say I call it pink is N, is it? Yeah, no, yellow is N.
No, pink is N. Pink is N.
Yellow is N, pink is N. Which one do you want to switch?
You want to switch it in M, so then U and W are exposed.
Yeah, I want to keep U and W exposed.
Exactly.
So that means I should choose I should not choose this edge, I should choose the yellow edges here. Right, I want to choose yellow here and everywhere else I want to choose pink. Pink is M. Yeah, good. Okay. So consider M star, which is M symmetric difference on this path. What this means is all the pink edges are as they are. On this particular path, instead of the pink edges, I will choose the yellow edges. Right? So let me draw this with orange. So orange is basically, here I will take the yellow edges. And everywhere else, it is the same as the original pink matching. That has not changed. No changes elsewhere. According to this, according to M star, which is my orange matching, what is W? W is exposed. What about U? U is not on this path because X is not equal to U. So therefore U is unaffected. It is also exposed. W is exposed. Let me reflect that here. W is exposed, U is exposed. But we just switched on an even path. Observe that switching on an even path gives you a matching of the same size. Right? Switching on an odd path doesn't do that. But we switch on an even path. Because all paths are even. Right? So now what we have is a maximum matching of G for which both of these are exposed. That contradicts our choice. We minimize the distance between the two vertices. Right? So we are done. We proved this statement and we agreed earlier that this was enough. So everything is done. Okay, so a quick summary, what we did is we proved the Tutte-Berge theorem, right? We proved it by induction on the number of vertices. If there is an essential vertex, we just finished the proof by induction. It was annoying, but it went through. And if there is no essential vertex, then every vertex is an essential. And we characterize these graphs. These are exactly the hypermatchable graphs. They have a barrier, the empty set. Even if your graph is not connected, it's just disjoint enough hypermatchable graphs. Therefore, the empty set is again a barrier. So these have a barrier, and that is the base case. The induction step went through. Proof is finished. Tutte-Berge theorem implies Tutte's theorem, and we use Tutte's theorem to prove Peterson's theorem and Schoenberger's theorem, which stated that every two connected three regular graph is matching covered. Every edge belongs to some perfect matching. Right? So what we will do tomorrow is we will prove tomorrow that every two connected three regular graph, the edge chromatic number is either 3 or 4. And to do that, we will prove a beautiful result in vertex colorings called Brooks theorem. Yeah? Alright, that's all for today. Thank you.